Okay, let me start off this clip by just mentioning that I made a mistake on the last clip. I basically drew this when the photon goes off at 90 degrees, the the electron can't recoil straight down, because then the x component of the 3 momentum wouldn't be conserved, because in this case we wouldn't have any x component of 3 momentum, and so the the electron has to go off at an angle like this. Okay. All right. Okay, before we move on, let me just give you an idea of the magnitude of this effect. Okay, so if you calculate this factor here, hc over mc squared for an electron. Okay, so hc over mc squared for an electron. This is the rest energy of an electron, which is 0.511 MeV, and hc can be put in a form, the Planck's constant times the speed of light, as 1240 eV times nanometers. So the whole thing here is equal to 0.00243 nanometers. Okay, that's an incredibly small number, right? So if you think about the wavelength of visible light, blue light, the transition between ultraviolet and blue light is about, and violet light is about 400 nanometers, and the transition from the red end of the spectrum to infrared is about 800 nanometers. So the whole visible spectrum is between 400 and 800 nanometers, and this shift is a 0.002 nanometers. So you can't use visible light to observe this effect, and in fact Compton used X-rays. These are very high energy photons with wavelengths in the range of less than 0.1 nanometers. Okay, so in that case, you can actually start to resolve these shifts, because they're these wavelength shifts, because it's a reasonable fraction of the wavelength. Okay, so what this Compton experiment shows very clearly and beautifully is that even though a photon has no mass, and even though the magnitude of its form momentum is 0, it still carries energy and momentum, and you can conserve its energy and momentum in these sorts of collisions. And the electron would not recoil as it does, and we wouldn't see this wavelength dependence that Compton did, and that we can recreate in the lab now, if the photon didn't carry energy and momentum. Now, we've talked about how the mass and energy are actually kind of interchangeable. Okay, and so a particle that has a rest mass of mc squared, that characterizes its internal energy, and in fact, when it can convert some of that internal energy into kinetic energy and other kinds of energy through processes such as decay, like if you have a fission process. Okay, so where does that leave the photon? So the photon has no rest energy, has no mass. Then what sort of so it has no internal energy, and so how does that relate to a mass? Okay, so we're going to a very nice sort of way to think about this, which comes from Hogg's notes on special relativity, is to think about mass transport by photons. So what we imagine is that we start off with a box of mass m and length L. Okay, and we imagine that this box is on a perfectly friction-free surface. So if you like, it's got wheels on it. The wheels are massless, and the wheels and there's no friction with on the wheels. So basically, this box can just slide back and forth at will with no friction. And then we imagine that we have a photon that is emitted from one side of the box and is absorbed by the other side of the box. And let's try to find out what happens.